Hi, this is lecture 1.2, Patterns in Nature. Let me share with you this PowerPoint presentation as we move forward to our lesson for today. The line of symmetry can be defined as the axis or imaginary line that passes through the center of the shape or object and divides it into identical halves. As we can see, the upper right corner, or the figure on the upper right corner, shows this figure in which it has one line of symmetry that could divide the entire figure into two. If we observe the object here, square, we could also see that it has four lines of symmetries, or four possible line of symmetries. In this object, or shape rather, we find at least two line of symmetries. For this one, we get around three line of symmetries, possible line of symmetries. On the last figure, we have at most possible 5 lines of symmetries. So what can you observe? How many lines of symmetry could regular shapes have, or regular polygons have? If we look at this figure, we see that triangle had 3, the square have 4, the pentagon have 5, the hexagon has 6, and the octagon has 8. So do you see a pattern? Yes, indeed. The number of sides, equal sides, reflects the possible number of symmetrical line that could be drawn in it. When it comes to nature, we see these objects also have its line of symmetries. The figure, the butterfly figure, have one line of symmetry. We could divide it here. This one had at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible line of symmetry. The flag, if we just consider the shape, could have 2, 3, 4 possible line of symmetries. The banana have none. The bicycle also have none. But this picture of the lynx could have a line of symmetry right here in the middle. So with this, we realize that a figure has a rotational symmetry of order n, where n is the fold rotational symmetry if 1 over n of a complete turn leaves the figure unchanged. So we could solve the angle of rotation is equal to 360 degrees over n. What do we mean by this? It meant that this figure could be rotated 5 times with the angle 72 degrees, and the shape would not change. This figure could be rotated on the center 5 times with 72 degrees turn, and the angle or the shape does not change. So the angle of rotation is 360 over n. 5 sides, 360 over 5 equal to 72 degrees. That's the angle of rotation. Moving on, we see these beautiful examples of figures or shapes in nature. The spiderwort is an American plant whose flower bear long hairy stamens, and we could see that this flower has a threefold symmetry, an angle of rotation of 120 degrees. Again, 360 divided by 3, 120 degrees. The starfish is a marine species of, or rather it's a marine echinoderm with 5 or more rotating arms, and it has 5-fold symmetry and an angle of rotation of 72 degrees. The snowflakes has a 6-fold symmetry with the angle of rotation of 60 degrees. So again, we could solve the angle of rotation by dividing 360 degrees with the number of fold symmetry a shape is given. So there's this beautiful shape actually, the honeycomb. The honeycomb is one of the unique shapes found in nature. Why unique? Because the hexagonal formations of the honeycomb produces optimal use of available space. The packing problem is the problem being shown to us today. It involves finding the optimum method of filling up a given space, such as a cubic or a spherical container. This is a very on-time problem, especially in this world today where packaging is very important. And it showed that hexagonal formations actually is the optimum shape could be used to provide optimum space, field space. Another example of patterns found in nature are tiger stripes and hyena spots. Also from zebras and Dalmatians and other cheetahs and other animals. These are patterns that is found in nature. And Alan Turing discovered that chemical reactions and diffusions processes in cells determine the growth of dots and patterns in animal. I would like to encourage you to watch video 1.2 and answer the following questions for activity 1.2. Another example in nature are sunflowers. These are beautiful, beautiful sunflowers. And the patterns of the seeds in sunflower actually is clockwise and counterclockwise arcs. The spirals extending outward from the center of the flower. So it is not a coincidence, but it has a purpose. This will allow the sunflower seed to occupy the flower heads in a way that maximizes their access to light and necessary nutrients. So actually this is still a packing problem. The leaves of the plants, it comes with many shapes. The Phyllotaxis, a special name to describe the growth of pattern of leaves on a plant. Leonardo da Vinci made observation of the spiral arrangements of plants. Although he did not leave behind too many comments, later on naturalists noted that spiral phyllotaxis of plants were sometimes clockwise and others or otherwise anti-clockwise, but it seemed to follow the so-called mathematical golden ratio. The angle between O japonica leaves are 180 degrees, 90 degrees, 180 degrees, and 270 degrees. And then the next leaf resets the pattern of 180 degrees. So even the leaves of this plant have its pattern. The shells of a protonode or the shells of a snail starts to be fragile, but it develops to be a hard home for this soft little animal. And if we zoom in towards the formation of this beautiful shell, we find equiangular spiral. As the distance from the spiral center increases, the aptitude of the angles performed by the radii to the point of the tangent, the point remains constant. So in short, it has a pattern that it uses a pattern even in the formation of the shell of the snail. And do you know what? This is also following golden ratio. Later on in the next topic, we'll discuss golden ratio in a much in-depth manner. The world population has also somewhat having a pattern as explained by this equation. P is equal to P naught E raised to the RT, where P is the total population after time T, P naughts is the starting population, or P sub 0. R is equal to the rate of growth. T is equal to time. And E is Euler's number, 2.718. Okay, so let's try to solve this world population problem. It states that the exponential growth model P is equal to 30e raised to 0.02t describes the population of a city in the Philippines in thousands. T is equal to years after 1995. So what was the population of the city in 1995? What was the population in 2017? And what will be the population in 2023? Let me share with you this whiteboard to try to solve this following equation. So we were asked to solve the population of a city in the Philippines in thousands if the growth model is equal to P is equal to 30 E raised to 0.02 T. So let's try to answer letter E. What was the population if T is equal to 1995? So since 1995 is the starting year, 1995 minus 1995 is 0. This is P equal to 30 e to the 0.02 times 0, which is equal to 30 e to the 0, which is equal to 30 e, or rather this one would be just be 1. So this is 1 because e to the 0 is 1. So P is just equal to 30,000. How about this one? When T actually is equal to 2017. So let's subtract 1995 from 2017. 2017 minus 1995. If you have your calculators with you, you could use your calculators. The answer is 22. So P is equal to 30 E point 0.02 times 22. So 0.02 times 22 is equal to 0.44. So this is 30 e to 0.44. And if we input that on the calculator, 30 e raised to 0.44, the value is 46,000, or rather 46, let's redo the, or undo this one, 46.581, which is equal to 46,581, since we're dealing with thousands as it was stated in the problem. So it's 46,581. So let's try again another one. How about when T is equal to 2023? So let's once again subtract 1995 to 2023. So 2023 minus 1995 is equal to 28. Or let's undo that one. 28. So we now have P is equal to 30. Let's make that somewhat clear. P is equal to 30 e raised to the 0.02 times 28. So 0.02 times 28 is actually 0.56. So we get 30 e to the 0.56. And if we input that on the calculator, 30 e raised to 56, or rather 0.56, we get 52.520 or 52,520. We always multiply this with 1,000 because it is stated in the problem that it is in thousands. All right? So how about let's try once again the next problem. Let's try a different problem. How about this one? P sub 0 is equal to 680,000. R is equal to 12% per year. And T is equal to 8 years. So what is missing? What is missing actually is P, because we have P sub 0. So let's try to solve for P. We know that P is equal to P sub 0 e raised to the R T. Now, we substitute the value. This is 680,000. Let's make that some, it's hard to write with the mouse. 680,000 e raised to 8%. That's 0.08 times t, which is 8 years. So 0.08 times 8, that's 0.08 times 8 is equal to 0.64. So this is 680,000 e to the 0.64. And 0.64, or rather, let's solve this one. 680,000 times e to the 0.64, right, is equal to 128,000, or rather 1,289,607. So this is the P, or the next population after 8 years. Let's try solving number 2. We are given P is, let me share with you again the question. P is equal to 1,240,000, R is 8%, and T is equal to 30 years. Now, we see this, we get that 1 million, again, let us refresh ourselves with the formula. P is equal to P sub 0 e raised to the R T. So we have 1,240,000. This is equal to P sub 0. That's what we're looking for. E raised to 0.08. That's 8%. times 30. So what we get is 240,000 is equal to P sub 0. Let's solve this one. E raised to the 0.08 times 30, which is equal to 2.4. Now we have 1,240,000 is equal to P sub 0, E to the 2.4 is equal to 11.023. So we get P sub 0 is equal to, we divide both sides with 11.023. So we get 1,240,000 divided by 11.023 is equal to 112,492. That is our solution. So hopefully you practice with the other questions or the other problems that we could solve, like question number 3, 4, and 5, and also some word problems in question number 2 here for world population. So that's it. See you again next time.